Okay, I want you to imagine three balls, three objects, three particles, whatever makes you feel good. Imagine three particles picked from a group of 1,000 particles. Three particles picked from a group of 1,000 particles. Now we need a way of recording this. We could use our fingers and toes, but eventually we'll run out of fingers and toes. So the best way to go about recording this data is to use sheets of paper. Now we are an advanced civilization. We're not going to waste our time scribbling on rocks. So we're going to be using sheets of paper, but we're going to be using the old way of recording data, that of using strokes. Now, believe me, this is a very, very effective way of recording or keeping track of information. Now, we can keep doing that, but eventually we'll realize that we need a shorthand notation so that we can keep track of certain information that occurs repeatedly in huge quantities, like comes in abundance repeatedly. That's why we have introduction, that's why notations like V and X were introduced. They were shorthand notations so that we don't have to occasionally write out 10 strokes. Now, this was a good number system. This is a number system. This was a good number system. But, we wouldn't be using our number system if it didn't possess advantages over the old number system. Now, let's look at our number system. So we've got the symbol 1, which stands for a single stroke, which stands for a single object. Keep that in mind. We've got 2, which stands for two objects, or two strokes. And then we've got 3. Now I want you to pay special attention now. I wrote 3, but I put 4 strokes. 4 strokes. That wasn't deliberate. That was a mistake. And we use 5 strokes for 10. Now, when I'm saying strokes, I'm also including the diagonals. But look at number 11 now. That's why I want you to pay close attention. Number 11. I'm saying not this. Why am I saying not this? The symbol we use for 11 is a shorthand notation, and it's spoiling people's brains. Other people's brains have been spoiled to the max. The right way of writing is 10 plus 1. That's the right way of writing 11, of picturing 11. It's 10 plus 1, not the 2 ones. The same applies for 12. The right way of picturing 12 is picturing 10 plus 2. That is the right way of picturing 12. 12 is just a shorthand notation. Please, brothers, please, sisters, please, fathers and mothers, whoever is watching this video, keep that in mind. The same applies for 13. I can go on and on and on doing this. The same applies for 13. It's 10 plus 3. 1, 3 is just a shorthand notation. Get that in your head. So from now on, whenever you see 11, 12, 13, think the way I'm writing them out. Now we go on to 20. The same thing applies. It's 10 plus 10. Please bear that in mind. Drill it in your mind. This is going to be very, very, very important when it comes to mastering multiplication. Now let's look at this rectangular array. This rectangular array of particles. Now, this rectangular array of particles has special features. What are the special features? It has 3 particles forming the breadth and 7 particles forming the length. All in all, it has 21 particles. Now, I want you to bear this in mind. Multiplication is simply the counting of particles that form a rectangular array. Special emphasis on rectangular array. Now, the counting is easy when we've got a few number of particles like the ones shown. But when you now have a rectangular array like this one at the bottom, that's a whole nother problem. Now look at this rectangular array. It could be a rectangular array consisting of 500, 10,000, basically a huge number of particles. Now, counting the number of particles in such a rectangular array it's like a mess. It's a mess. It's a huge problem. So, though multiplication is counting the number of particles in a rectangular array, we need a way of making the counting process easy. And how do we go about that now? Now, in order to make the counting process easy, what we do is we select a few rectangular arrays and capture their features, their information, what makes them unique, which of course we know is the length, breadth, and the total number of particles. So that's what we do. We capture that information and tabulate it. Remember, we only need a few number of rectangular arrays. For example, a rectangular array with a length of 1 and a breadth of 1, which all in all is just one particle. A rectangular array with a length of 1, a breadth of 2, which all in all are 2 particles. And so forth, touching again on length of 7, breadth of 3, like the rectangular array we saw. Now, if you look at my table, that's just a conventional common table. Now, we can use a different kind of table to record the same kind of information. And this is the table you have been acquainted with since primary, the ones your teachers have been drilled into your head in primary. And I want you to always keep this in mind. That table captures the same kind of information. Now take a close look at this table. This is just the familiar times table, like I said. Now we've got the breadth on the left, we've got the length on top. You can switch it, you can exchange it, that's fine. Now, this is how it works. We've got the breadth on the left, the length on top. Where is the column for the total number of particles like we had in the first table? The total number of particles are now put inside the space. If you look at the diagram, I wrote total particles and I pointed at 6, which shows that a rectangular array with a length of 3 and a breadth of 2 has a total number of particles like that amounts to 6. So the times table you were taught in primary was really just teaching you how to look at rectangular arrays. But it's a pity they didn't tell you that that's what they were teaching you. But that's all in all what they were teaching you. That's what they were drilling into your mind. So now whenever you see an expression like 3 times 7 is equal to 21, always think rectangular array. That expression is simply a shorthand. For example, 3 times 7 is equals to 21. It's simply a shorthand, a way of saying we have a rectangle consisting of 21 particles, which has a length of 7 and a breadth of 3, depending on whichever you're calling the length and the breadth. That's all. That is all there is to multiplication. However, take note that the multiplication table doesn't deal with huge numbers. It only deals with small numbers. So how do we go about multiplying huge numbers, say like 240, for example, times 30? How do we go about multiplying that? Now, that's where logical reasoning comes in. The multiplication table teaches you to memorize. Then from there on, in order to count a huge number of particles, it's simply now a matter of logical reasoning. Let me show you how. Using that expression of 240 times 30. So in order to solve for 240 times 30, we draw our rectangular array. Now keep in mind, in practice we won't do this. This is just a way of showing you the framework or the backbone of multiplication. So we draw our rectangular array with a length of 240 and a breadth of 30. Now remember what I said, 1 1 is simply a shorthand for 10 plus 1. Yes, the same applies to those huge numbers. 200 plus 40 is a breakdown of 240 being a shorthand, 30 again being a shorthand, the breakdown being what you're seeing on the right. So using these, we can split the rectangular array into little rectangular arrays. Like we've got 3 rectangular arrays of 200 by 10 and 3 of 40 by 10. So if we go down to the expression, we've got 240 times 30 is simply 200 times 10 plus 200 times 10 and so on, and then 40 times 10 plus 40 times 10 and so on. Keep in mind that the 200 times 10 in the expression are representations again of rectangular arrays. So we can keep going, we can keep forming smaller and smaller rectangular arrays. Now the expression that follows below is a further simplification of the expression above. So the 200 times 10, the 200 times 10s are simplify further to 10 times 10 plus 10 times 10 plus 10 times 10 plus 10, including the 40 times 10. They simplify further to 10 times 10, 10 times 10, 10 times 10, 10 times 10. It's all a matter of simplifying it up until you reach the point where you can now use the multiplication table. So all in all, when you reach the point where you can now use the multiplication table, then you're good to go. So 10 times 10, we know from the multiplication table that that's 100. So we now substitute 100, 100, 100. Then if you remember the counting system, 100 is simply 10 plus 10 plus 10 up until we have like 10 tens. So all in all, we'll have a chain of 10 plus 10 up plus 10 plus 10 plus 10 plus 10 up until we get the correct answer. That's the framework behind multiplication. So that's it, guys. Thank you for watching, and please, if you enjoyed the video, please leave a like, and if you want more content like this, please subscribe and leave a comment. Please do not hesitate to leave a comment in the comment section. Thank you very much. Watch out for the next video. It's going to be interesting as we progress interesting videos. I'm going to be producing more interesting videos, so please don't miss it.